Hello and welcome back to Oceanography for the final time this semester. So today we're going to finish up Module 5 talking about the future. Obviously this isn't in the textbook and there's a lot of speculation in this, so there won't be a lot of stuff on the final related to this topic, but it might be the only science course that you take in your time at Oswego, so I figured it'd be an interesting topic to finish up on. Just remember also that the final exam is next Thursday, December 3rd. So some last announcements here, and then that's going to be the end of the class. So congratulations for making it this far. One more lecture to go, so let's get into it. But first, let's talk about what we did last time. So the most concerning part about anthropogenic climate change is what? So take a look at those options there. What do you think? A 3, a 2, a 1, a 0. So the real concerning part is really the rate. We are causing it. In many ways, that's good, though, because if we're causing it, if we're the problem, we can also be the solution. It remains to be seen whether we'll do that or not, but it's kind of in our hands. We have control over it to some degree. The magnitude, it's not the hottest it's ever been on Earth. It's going to be a long time before it is. It's the rate that it's changing. Nature can't keep up. And I would say that we do understand it pretty well. The physics are relatively simple. Carbon dioxide is a greenhouse gas. We're putting carbon dioxide into the atmosphere. The greenhouse effect is increasing. We're storing more heat and the globe is warming. So that's pretty simple. All right, the most agreed upon start of the Anthropocene was or is, so where would we start this Anthropocene era? The age of humans. So from a scientific perspective, it would be 1950 because that's the easiest to date. It's when we really start impacting. It's the start of the Great Acceleration, and it also has an excellent geologic marker in those radioactive elements from the nuclear bomb tests. Okay, so Earth has been on a 4.6 billion year journey to get where we are today. So if we go all the way back to the start of the universe, this number keeps kind of changing a little bit, but it's somewhere around the neighborhood of 14 billion years ago. The singularity expands outwards from the Big Bang. A precursor solar system to us went supernova about 6.6 billion years ago. And then our sun and the planets coalesced from that supernova about 4.6 billion years ago. So the age of our Earth is about 4.6 billion years ago. This is oceanography, so when did we get our oceans? The answer is a lot sooner than we used to think. Probably pretty close to immediately. As soon as the Earth cooled enough for water to condense into clouds and precipitate out as rain, that's probably exactly what happened. And so there's pretty strong evidence that oceans were around probably within the first like 200, 300 million years of Earth's existence, definitely by 4 billion years. And so we followed up this path and through the Precambrian, we didn't really go over a lot of these geologic time names, but through the Precambrian, it's really just single cell things, really just those cyanobacteria pumping oxygen out into the air. And it's only when we get into the Cambrian period at the start of the Paleozoic that we have multicellular organisms. This Paleozoic is sometimes called the age of the fishes. At the end of the Permian, we have this mass extinction. These early amphibians and things go extinct, and it ushers in the age of the reptiles, most famously the dinosaurs, and the flying reptiles like pterosaurs, and the swimming reptiles like mosasaurs and ichthyosaurs. And then at 65 million years ago, there's another major mass extinction, ends the age of the reptiles, enters into the age of mammals. Mammals start dominating the lands, and eventually they even start saying, hey, let's go back into the oceans, and we have marine mammals. And that brings us to today. And again, are we entering into the Anthropocene, the age of humans, where humans are the defining creatures on the Earth? We talked about that last time. So let's talk about the future. Where are we headed? So there's a whole genre of books, films, movies, pop culture trying to predict what the future might look like, and people have been at it forever, ever since we became like aware of the concept of time. We were kind of trying to figure out where things might be headed. So these are some pictures from about 1900. These are postcards from a fair, and it was a future fair. They were asked to predict what the future would look like in the year 2000. So this is 100 years, and this is what they came up with. So do we see this kind of thing? Not really. So these are a bit off the mark. So these crazy contraption flying machines, personal planes like this, do we even really want this kind of stuff? This looks pretty dangerous to me. Again, at the time, like a lot of steam shipping, railroads were a big thing. And so you kind of, what's going to happen in the future? Well, trains and boats are a big thing. What if we combined them together? So this is a pretty good illustration of like how limited our foresight can really be. We're somewhat limited to the concepts that we're familiar with, and we just kind of paste them together into this weird amalgam. None of these really predicted like the internet or computers or anything like that, because there wasn't anything even remotely like that. It was just unfathomable. And then this is probably the funniest one, a unicycle water wheel and these balloons that help you walk on water. Even the horse is getting into the action. Okay, I'm not sure why we would even want to do that, but that's what the future looks like to some people. The real problem with predicting the future is that just like evolution in organisms, evolution is very rapid changes, and then often it sort of plateaus as a stasis, and then another very rapid jump and change, and then more stasis. This is how technology evolves. So think about like computers. Computers started out really slow, they evolved slowly, and then they really just kind of took off. And now we're starting to bump up against some limits, which we'll talk about later, starting to kind of potentially maybe plateau again. Or you think about the internet. Initially, the internet was very slow to be adapted, and then it really just took off. Now everyone pretty much has access to internet. It's starting to plateau off. So what's the next disruptive thing? We're very bad at coming up with that. We're limited by our imaginations and what we know and our experiences. All we can say about predictions of the future is that they're almost certainly wrong. Now, there's a lot of things that have come true that were predicted, but you can see that a lot of these things are kind of off the mark. So anything that I say in this lecture today is likely to be off the mark to some degree. So that's why it won't be on the test, but it's just interesting. So let's talk about the very near future. In the near future, our biggest challenge is probably going to be our growing population. So last lecture, we talked about the Anthropocene and all the impacts of the Anthropocene. As the global population increases, that's just going to expand those consequences. So the Earth technically can support about 2 to 3 billion people at the standard of living of the OECD, the quote-unquote developed nations, although that's not a very good term. About 2 to 3 billion people at that standard of living. Now, if you back up like a century, we would say that the globe can't even support 2 to 3 billion people at that standard of living. And so science helps us along, technology helps us along. This might be kind of short-sighted, but with current technology, with current way we do things, we can support about 2 to 3 billion people at like our standard of living. So how do we respond to increasing population? Well, fortunately, the population has been accelerating rapidly, but it is starting to plateau off. So it's not going to reach the kind of highs that were predicted as recently as like a decade or so ago. It is starting to kind of turn over, and we're flattening the curve. Everyone's very painfully familiar with that term now. But the big problem is, okay, well, there's going to be a scarcity of resources. How are those resources divided? And the answer now is very inequitably. It's not equal. It's very disparate distribution of these limited resources, and that leads to problems. That leads to conflict. That leads to strife and inequality. So how do we deal with that? That's going to be one of the major themes of the future. But you can see here the world population growth through time, very stable, very slow growth. In some cases, even dips due to really big things like the Black Plague, the bubonic plague, and then just takes off at the Industrial Revolution and at the Great Acceleration, unprecedented rates of change. We've gone from 1 billion people to 9 billion people in 100 years, 120 years. Just ridiculous. The rate of growth is unfathomable. So that's kind of the near future challenges. We already talked about water resources, we've talked about pollution, we've talked about resource extraction. All those things are going to be problematic in the near future. But we're going to start taking a look at kind of the more outward future. So what could happen to us? So there's really, I liked this article that Bostrom wrote. It really kind of categorizes us into 4 different possible categories. One is extinction. So that's the pretty pessimistic view, you know, like Planet of the Apes. You maniacs, you blew it up. Damn you all to hell. Are we going to blow ourselves up? That's certainly a possibility. Since 1940s, when we invented the atomic bomb, we now have the ability to wipe ourselves off the face of the planet. That's not something that any other species has been able to do before, and it's obviously painfully close at times. Disease, climate, just natural disasters like a meteor impact, or eventually the sun is going to burn out. The sun's about halfway through its fuel. If we don't leave our solar system by the time that happens, we're going to go extinct. I feel like 3-point-some billion years would be a pretty good run for us, but we have a limit here. So extinction is one possibility. I'd like to think that we're smart enough that we can avoid that, but we'll see. Another thing is plateauing, where we maintain our current standard indefinitely and we don't really advance. That's never really happened in the history of humanity. We've always kind of had this steady progress. There's been a couple setbacks along the way, but we're always kind of moving forward, improving our technology, and every generation teaches the next generation. Just our language and our ability to pass on our experiences pretty much makes plateau very unlikely. It's really unlikely that we would just kind of flatline. It's much more likely that we either have a dramatic decline or a dramatic increase. Another thing is recurrent collapse, where we kind of occasionally have these big events where we kind of have a big setback and then we recover, and a big setback and we recover, and then we kind of keep yo-yoing back and forth from a very advanced civilization to a lesser advanced civilization, and we keep kind of doing that over and over again without ever learning from our mistakes. And then probably the more optimistic scenario is that we kind of transcend humanity and move on to a post-human condition. This would be like true immortality. The human race would be immortal. It would not be possible to kill us. We would transcend our physical bodies, transcend Earth. One way to do that is just kind of merging with machines, the AI singularity, or the ability to move out of our solar system, interstellar colonization, so that when the Earth ends, when the sun ends, we're no longer here, or at least not all of us are no longer here, and then maybe even traveling to other galaxies and really expanding our footprint. And at that point, there would be no way for us to be wiped out. If the Milky Way galaxy happened to be destroyed, we would still be fine. There would still be some of us. So these are kind of the 4 interesting scenarios. Which one do you favor? Post it in the comments what you think. So artificial intelligence is probably, it's becoming more and more relevant. Machines have been getting faster and faster and faster. There's this thing called Moore's Law, where transistors, the size of transistors halves every 2 years, which means that computers shrink in half every 2 years and their speed doubles every 2 years. So like I have in my pocket a smartphone. This smartphone that fits in my pocket is well beyond the computing power of those massive warehouse-sized computers that put people on the moon in the 60s. It's just this ever fast-changing march. Just think about the computers that you grew up with, the big chunky desktop computers. Now everything's tablets, phones, laptops. Technology is getting smaller and faster. One thing that's sort of interesting, though, is that this increase has sort of fueled our technological advancement, and we're starting to actually bump up against some physical limits. We're starting to have transistors that are so small that we're actually starting to be limited by the physics of the size of the molecules and the atoms. There's only so small that you can actually make a transistor, and we're getting to that limit now. So in order to get to the brain power equivalent of a human, which is, it appears to be pretty close to within our reach using Moore's law, we're going to have to solve these physical limits. So one thing that we might be able to do is move towards like neural networking computing and sort of do away with the old transistor style. Again, the way that the future happens is these disruptive stepwise changes. This is a progressive advance, a very fast progressive advance, but the future is probably a step change away from this, something completely different that we have trouble fathoming now. And if we're able to get machines that are on the order of our brain power, we have created intelligent machines, or spiritual machines, as Ray Kurzweil put it, the age of spiritual machines. Our Lady Peace thought that was cool, so they made an album about it. But at that point, then the lines between humanity and artificial intelligence kind of start to blur and merge, and that would be the AI singularity, and that's what could maybe push us towards that immortality scenario. Pretty scary stuff, pretty interesting stuff, a lot of possibilities for the future. What does the future of Earth itself look like? So we've talked about plate tectonics earlier in the semester. We talked about convergent collide, divergent divide, transform, slide. Those things are ongoing at all times. We know the direction the plates are currently heading. We know how fast they're moving, and we can calculate where they'll be in the future. That's not quite so simple because they can change. So like when we were looking at plate tectonics, we saw that the Hawaiian Islands and the Emperor Seamount, there's a very angle change there. The rates and direction can shift, so it's not quite as simple. We have to make some educated guesses about what's going to happen, but what we do know is that the Wilson cycle, the supercontinent cycle, is going to continue into the future. And so this is what Earth is probably going to look like 100 million years from now. Some differences that you'll notice, there is no Mediterranean Sea. The Mediterranean Sea has closed. Africa has fully collided with the Eurasian continent, and the Alps are now this massive, they're already very massive, but they're this massive mountain chain. You'll notice that the Himalayas are a little bit eroded away. So the Himalayas are currently actively being built as India smashes into Asia, but now that the continent is sort of docked, erosion is going to start taking place over uplift. The Himalayas are going to start being weathered away, and now the Alps are probably the largest mountain range on Earth. You'll also notice that Greenland, there's no ice on Greenland. There's little to no ice on Antarctica. All the glaciers have melted. Major river valleys on Earth are flooded: the Amazon, the Congo, the Mississippi Valley. Hudson Bay is flooded. Florida's underwater. All of that ice melting is like 70 meters of sea level rise. And so a lot of stuff is underwater. The East African Rift Valley is gone to completion, or it's opened a new mini ocean basin, and Somalia is drifting away from the rest of Africa. There's a lot of changes here, and this is pretty well established. If we keep going further into the future, that supercontinent cycle will complete, and we're going to assemble another supercontinent. So we talked earlier in plate tectonics about how we always talk about Pangea, but Pangea wasn't the first supercontinent, and it's not going to be the last supercontinent. Right now, the Atlantic is opening, and the Pacific is closing. And eventually, there's already some evidence that the Atlantic is opened up as wide as it's going to get. There's some evidence that the plates near like offshore Portugal, offshore Spain, that the ocean crust is starting to kind of break off to maybe start a subduction zone and then start closing the Atlantic Ocean. So it's really what the future looks like is kind of a debate about whether it's the Atlantic basin that closes or whether it's the Pacific basin that closes. What that's going to change the outcome. I kind of favor the Pangea Ultima scenario where the Atlantic basin is the one that closes, and then that results in this kind of configuration here. This would be us here, the star. We would be in the interior of sort of this massive continent. It would probably be very dry, very difficult conditions, just like it was with Pangea. That's probably what will end up looking like. And you'll notice again all these massive mountain ranges where the continents have collided, convergent, uplifting mountain ranges. So that's probably about 250 million years away. And then that's just going to happen again. So these continents are going to break apart and it's going to start all over again. The Wilson cycle will keep going. Oceans will keep opening, expanding, and then being old and closing. But eventually, Earth is going to come to an end. So the way that the Earth will ultimately end is that the sun is ultimately going to end. Our sun has been around for about 4.6 billion-ish years. It's got about that much fuel left. It's about halfway through its life cycle. So what's going to happen with a main sequence star? So this is a very famous plot with surface temperature and luminosity, and our sun is right here. It's a relatively average temperature star. It's a relatively average luminosity star. It's a pretty typical main sequence star. And what happens to main sequence stars is that when they run out of the hydrogen gas fuel, they initially shrink. So there's a balance with a star between gravity pulling stuff in and the fuel reaction pushing stuff out. Right now, the sun is in pretty good balance because its gravity is trying to push it in, but the fuel furnace is kind of pushing it out. When it kind of runs out of the hydrogen fuel, it starts shrinking, and gravity really starts taking over, and it's able to start fusing heavier and heavier elements all the way up to iron. And as it does that, it starts expanding. It expands to what's called a red giant. A red giant is massive, so massive that the sun will actually expand past Earth and almost all the way to Mars. Earth will literally be engulfed in the sun. And long before that happens, all of the atmosphere will be stripped away, the oceans will be evaporated, all life on Earth will be vaporized, and eventually the planet itself will be vaporized. Once all that fuel is fused, the sun contracts to a white dwarf. There's a nebula. The gases and materials are sort of scattered out into the cosmos and would be recycled into the next solar system. And the sun itself would eventually cool and become a black dwarf, and the cycle starts all over again. So pretty interesting scenario. Obviously, we don't want to be here when that happens. There is no way that we could survive being engulfed in the sun. So if we're going to survive past the lifetime of the sun, we have to get away. So there's a couple different civilization types, and they're based on how much of the energy around them they're able to control. Right now, we are a planetary type civilization, a type 1 civilization, or at least we're heading there. We're not quite there yet. A planetary civilization is able to harness all of the energy that falls on it from their planetary star. And right now, we're restricted to this environment. If something happens to our planet, if something happens to our sun, we're doomed. So we are slowly advancing towards this type 1. We're currently at about 0.72, but it's a log scale, so we're not as close as that maybe appears. To get to a type 2 civilization, you have to create what's called a Dyson sphere or something like it that actually harnesses all the energy coming off of the sun. And then the type 3 civilization, a galactic civilization where you're able to harness all the energy of your entire galaxy. We have some conceptions of how you get to type 1. It probably relies on fusion or antimatter, but we can kind of conceptualize how that could happen. We sort of envision what a Dyson sphere might look like. Obviously, the technology to actually build one is a long ways off, but we can sort of envision it. What technology that looks like to capture the energy of an entire galaxy, like, can't even really fathom it. So this is a long, long, long way off. Maybe not even really technically possible, but maybe someday we'll see. But if we make it past type 1 planetary and we're able to harness the power of the sun and leave our solar system, then we have the potential to become immortal beings where the human race will never die off. We're not at the mercy anymore of the whims of our planet and the lifespan of our sun. So that raises the question of, is there anyone else out there? Are there any other civilizations that are going through this same process? So we've been actively looking for aliens for decades now, and there's still no definitive signs that they exist. So there's a lot of reports occasionally. We've all seen those videos of the weird flying objects and all the like abduction reports and things like that. They may, in fact, we may have already been contacted, but there's no definitive, strong, concrete evidence that anyone would point to that makes us 100% believe that they're out there. But SETI has been sending radiation out into space since the 1970s. Ever since we started broadcasting radio in the early 1900s, we've been sending signals out into space. And so we've kind of been sending out like, hello, hello, hello. Is there anybody in there? It's been slowly moving through space at the speed of light. Electromagnetic radioactivity moves at the speed of light. And it's been happening since about 1901. So there's about 120 light years into space that our radiation has moved. That sounds like a lot, but the Milky Way is 100,000 light years across. So if we look at the Milky Way, this is our spiral galaxy. We're out here on one of the outer spiral arms, well away from the center of the galaxy where there's a lot of dangerous things, which is very fortuitous for us. How convenient. This little blue dot is how far our radio signals have traveled. So not a lot. 100 light years sounds like a lot, but it's really not in the grand scheme of things. But there are many stations. So this is the Arecibo telescope that was set up in Puerto Rico to monitor for any kind of signals. Unfortunately, it just collapsed very recently, and it's probably not going to get fixed. And so that's kind of the end of an era. But we've been listening since the 70s with no luck, except for one very weird pattern that was actually seen in 1977. It's called the wow signal, because whoever wrote it down wrote in the notes wow with an exclamation point. At the time, the telescope was pointed at this constellation Sagittarius, the Archer. And so was it actually a message? We were never able to repeat it. It was never heard again. It was never able to be seen, but it was some systematic pattern that didn't appear to be natural. It wasn't part of the natural background radiation, but it was one anomaly in the 50 years that we've been looking, but still pretty interesting. So we've been asking ourselves this question for as long as we've been able to really ponder it, is, are we alone? Are we the only intelligent life out there? So one way of kind of trying to figure this out is using the Drake equation. So it's not really an equation so much as it's a thought experiment about, like, what is it that would define the number of intelligent civilizations that are out there. So what we do, the number of civilizations in our galaxy with which communication is possible is the n. That's the answer. The only thing that we know about the answer is that it's not 0. It's at least 1, because there's us. And so none of these terms are 0, because if any of these terms are 0, they're all multiplied together, and you would get 0. We know that all of these terms are not 0, because there's at least 1, which is us. Another thing that's interesting is that some of the factors have gotten much larger over time. So we used to think that there weren't a lot of planets, for example. When I took high school Earth science, there were 9 planets in our solar system, and that was it. Now there's like over 4,000 exoplanets that have been recognized. So if we look at the Drake equation, the number of civilizations that should exist in our galaxy is the average rate of star formation per year in our galaxy. So how many stars are formed per year, really a proxy for how many there are. The fraction of those stars with planets, again, we used to think that maybe the sun was the only star that had planets. That's definitely not true. We observe planets on lots of other stars now. This number has gotten a lot larger. The average number of those planets that may develop an ecosystem, so an actual ecosystem like ours, the number that succeed in developing life, so actually going to that next step of life, and then of those planets that develop life, how many develop intelligent life, how many that develop intelligent life that are able to communicate interstellarly, and then the average length of time that they're around for and the chance that we would actually observe them. So multiply all these factors together and we should get the number of civilizations that we should be seeing or able to communicate with. So it's very interesting that really, if we think about it, most of these factors are probably a lot higher than we initially thought. And we know that it's not zero. If it's not zero, why would it be only ones? Given the number of stars that are out there, the number of planets that are out there, the number of planets that reside in the habitable zone of their stars, the number of planets that probably have liquid water, that probably have the conditions to sustain life, why would Earth be the only one that would develop intelligent life? It's almost weirder to think that we're unique than that we're fairly common. But there's some arguments against that. So one book that I read a while ago that was very intriguing was Rare Earth. So it talks about the rare Earth hypothesis. And so Earth, we like to say that the sun is a relatively ordinary main sequence star. There's nothing super special about the Earth. It's just a rocky planet that happens to be a special distance away from the sun. But there actually are some ways that Earth is very sort of not unique, but rare. There are a lot of happy circumstances of Earth that make it perfect for us. Now, that kind of begs the question, like, was it designed for us? Well, it appears that way because everything's sort of just right for us. However, if things weren't just right for us, we wouldn't be here. So it's kind of a circular argument. The reason that things are perfect for us is that things were perfect for us and we developed. If things were not in those conditions that didn't favor our development, we never would have had our development and we wouldn't be here asking the question. So we need to be careful about that. We need to be careful about making those weird circular logic problems. But some ways that Earth is very kind of different is we're in the proper kind of galaxy. So the spiral galaxies like the Milky Way are probably very prone, they're relatively stable, good for developing long-term solar systems. And we happen to be in a really low risk position, lower risk out on the outer spiral arm, away from all the crazy explosions and gamma ray bursts and all that stuff in the center of the galaxy. We're also the right type of star. It's a main sequence star. The right size of star. It's big enough to support long-term development of a solar system. And we're also the right distance. We're in the Goldilocks zone. We're just far enough away and just close enough that we've got the right balance that water exists in all 3 phases. Another thing is that we have an oddly large moon. So the oddly large moon stabilizes our axis. It produces the tides. And all of these things, both of those things, really could possibly contribute to the development of life. And we also have a very large gas giant neighbor in Jupiter, which shields us from big impacts. So not all of the big impacts, as we saw with the end Cretaceous Chicxulub impact, but Jupiter acts as kind of a solar system bodyguard. It sweeps up a lot of the bigger asteroids that are out there and sort of protects us. We have just the right tilt to give us the seasons. We've had very few major impacts. The existence of tectonics. Tectonics helps to regulate things, weathering and erosion, and all those other various cycles help to contribute to kind of the homeostasis of the Earth. It doesn't let it get too hot. It doesn't let it get too cold. We have oceans and we have our atmosphere, and our atmosphere has been modified by the living creatures to give us breathable oxygen. All of these things are probably not unique, but they're also not probably very common. And so the numbers for the Drake equation probably aren't quite as high as they would first appear, but they're certainly not zero, and they're probably not huge. But as we see, life finds a way. No matter where we look on Earth, we find living organisms in places that we wouldn't really consider. And so the Drake equation also sort of begs the question, we're looking for life as we know it. Is life evolving elsewhere as we don't know it? So life on Earth is carbon-based. Silica behaves similarly chemically. Is silica-based life possible? There's a lot of things, a lot of kind of problems with that, but is it theoretically possible? Are we looking for the wrong things in the wrong places? So that raises another question. So if there are a bunch of civilizations out there, if the Drake equation is not zero, which we know it's not, if it's not one, is it 10? Is it 100? Is it 1,000? Is it 1,000,000? If it's more than one, where are they? Why haven't we found it? So even if all those fractions are really small, there's 100 billion stars in the Milky Way alone. Multiply 100 billion by some small fractions and you still have a pretty big number. The other thing here is if intelligent life is not unique, if we're not the only ones, it's probably pretty common. If it's not one, it's probably millions. So where is it? Where are all these other civilizations? So these are a couple of the different explanations. One of the weirder ones is that we're just an illusion. Life is an illusion. We live in the Matrix. It's just a computer simulation. Reality is an illusion. Okay, fine. It's not super helpful. It may in fact be true, but it doesn't make any predictions. We're just not able to really talk. We're trying to communicate in different ways. We don't understand each other. We're using radio waves. Do they understand what a radio wave even is? Are they trying to communicate in some other way? Are we listening and talking in different ways? Or alien civilizations kind of know that we exist. They may even have put us here, and they're just kind of observing us from afar, and we're just kind of like this zoo exhibit for them. Or is it kind of like this very pessimistic kill or be killed, where we're not hearing anybody, we're not communicating with anybody, because anyone that starts sending signals out into space to let other people know they're there is very rapidly killed off. So is there some hostile species out there that everyone else is trying to just hide from? And they're like, oh my God, I can't believe Earth is broadcasting radio signals. What are you doing? You're going to die. Or space is just too big. You saw on that Milky Way galaxy diagram, 100 light years is not very much. It's very unlikely that we have sent our signal out far enough for anyone to pick it up. Or they're already here, they live among us, we just don't notice, we don't understand. They're very stealthy and they're trying to avoid detection and they've been here all along and we just don't know. Or we're looking in the wrong place or the wrong type, or they're very advanced and we are not able to perceive that they're there. Or we actually are the aliens, so the aliens have been here, they kind of dropped us off and just kind of left it on its own, and they're not interfering, we're just kind of like this planetary experiment. And the last one is that life is just extremely, incredibly rare, perhaps unique. Again, this is probably unlikely, but certainly possible. And so that brings us to the concept of the great filter. So if intelligent life is actually rare, but not unique, there must be something that kind of filters it out. And so our future, where we're heading as a species, is kind of dependent on where this filter is, or when this filter is, I should say. So the first option, option one, is that there's the origin of life. There's some common evolutionary steps. So going from single cell to multi-cell, going from multi-cell to actual animals, going from animals to intelligent animals. There's a couple common evolutionary steps. We know that that can happen, so we know there's not really a huge barrier to that. This is probably the most optimistic scenario where there is a great filter in the universe, something that when organisms get to this level of advancement that we're at now, they tend to be filtered out. One possibility for this is technology. Once you get to the ability to communicate with other stars and get into space travel, you've also invented the atomic bomb. You've invented the ability to annihilate yourselves. Is that the great filter? And we are currently past that great filter. So we haven't annihilated ourselves yet, but maybe other civilizations have. Another one is that the great filter is behind us, we've passed it, and so have a couple other species, maybe only one other species, and we just haven't been able to find each other yet. Option three is that there is no great filter. We're just kind of way out ahead in the race, and that we're trying to communicate via radio signals in space, and no one is that far yet. So maybe the most advanced civilization is like a proto-humanoid kind of race. And again, we're sort of, or at least I am, putting our human bias on this. Intelligent life doesn't necessarily have to be humanoid. It doesn't have to resemble us really in any way. So I feel like a lot of times our sci-fi is kind of restricted to that, in that, you know, with very few exceptions, alien species are depicted as mostly humanoid, maybe add like an extra eye or an extra couple limbs or something, but generally act and behave like humans. Option four is that the great filter is actually ahead of us, and that maybe some things make it through, but are we going to make it through? Well, it's the great filter, so it's highly unlikely. So this is probably the more pessimistic scenario, is that there is some catastrophic thing in the waiting for us ahead, and it might be that this civilization that's way ahead of us is hostile, and as soon as we become a threat, they will wipe us out. So again, pretty pessimistic. So how do we become immortal? So again, the Earth has finite resources. It has a finite lifespan. Hopefully we're not near the end of those resources, but eventually, if we're going to survive forever, we need to leave the Earth because the sun is running out of fuel. Billions of years left, but eventually it's gone. So the first target, we need to figure out how to settle inside the solar system. So where are we going to go first? So we need to figure out how to live outside of Earth. So where do we want to go to try that? So do we want to go to the moon? Do we want to go to Mars? Do we want to go to Venus? Ultimately, this doesn't really solve the ultimate problem. We still need to leave the solar system, but this is the first step. We talk a lot about Mars, establishing a surface colony on Mars. A couple challenges is that the gravity is much lower than Earth, doesn't have a magnetic field, there is no atmosphere, or very little atmosphere anyways, and the temperature is not really ideal, but there's a solid surface there. In many ways, Venus is potentially better. Venus has about the same gravity because it's about the same size. It's got a protective magnetic field. The atmospheric pressure is very high at the surface, but if you get up to a certain level in the atmosphere, you can find a place where it's equal to Earth's atmosphere. And so in many ways, a cloud city in Venus might be easier and potentially better than Mars, although you don't have any way of really getting abundant materials. So that might be a problem. But it's probably a good first step. So we talk a lot about Mars, but maybe we're forgetting a little bit about Venus. And then once we do start a colony, if we don't want to live in the bubbles forever and ever, we want to kind of try to make that planet into Earth, and that's called terraforming. So Mars doesn't have a real good atmosphere. Can we make one? There's very little, if any, liquid water available on the surface of Mars, but there is ice at the poles, water ice at the poles. perhaps water ice underneath the surface. It's possible that at times it even flows on the surface. But how would we make an ocean on Mars? So that's terraforming. That's something that we might be able to get to. And then eventually we need to get out. We need to get away from the sun. The sun will burn out. Earth will be consumed by the sun as it expands. To live forever, we have to get out of here. Our current status of rockets doesn't work. We can't build like an Apollo rocket to leave our solar system. It's not enough. So ion propulsion is one relatively new technology. It's already been used. So the Dawn probe, launched in 2012, it used ionic propulsion to visit Ceres in the asteroid belt. It's a lot faster, and it requires a lot less propellant than chemical, so it's a lot more efficient than rocketry. Basically, just electric charges are repelling positive ions, and those ions over time build up thrust. Another thing that hasn't really been fully evolved yet is a solar sail. So solar sail is like a massive light membrane, and as photons hit that membrane, it sort of accelerates it forward. It's using the radiation pressure from those light particles to kind of push it forward. So there really is no onboard fuel source. It's using the fuel of the sun in the area to kind of push it and accelerate it. It accelerates very slowly, but there's very little friction, and so it keeps going and accelerating and accelerating and accelerating. So that's an interesting way of possibly in the future getting out of here. But so far, the only thing that we've actually sent out of the solar system are the Voyager probes. So Voyager 1 and 2 launched in 1977. Voyager 1 left the solar system in 2012, and Voyager 2 left it in 2018. And in their payload, they have these golden records. And so recorded on here are sounds of Earth. So there's some blues music in there. There's some nature sounds. There's some nudie pictures of us for the aliens. There's some maps to where we're located based on the hydrogen atom that presumably would be communicable or understandable to any species that's scientifically advanced that would read that. But probably the coolest thing about this is that gold is relatively chemically inert. It's going to be floating out into space for essentially forever. Long after humanity is gone, if humanity is gone, these records are going to survive. And so we have made an indelible mark on the universe. This is going to be floating around in interstellar space essentially forever. I like this picture here. As the Voyager was leaving, it kind of tilted back and took a picture of Earth, the Voyager 1. It turned around, it took a picture of Earth, and people started looking at the image, and they're like, they expected the blue marble, like where okay, I don't see it. They looked a little bit closer, and they saw this little tiny dot here. That's us. So as Carl Sagan says, look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being that ever was is on that dot. This mote of dust suspended in a sunbeam, it really kind of puts into perspective how big the solar system actually is. And remember that the solar system is only a very small part of our galaxy, and the galaxy is only a small part of our universe. And so we're all on this little dot here, flying through Earth on space, flying through space on spaceship Earth. And again, this is kind of a tale to remember that we're all in this together, and to be a little more kind with each other. So how does the universe end? How does it all end? So there's a couple different things. There's the big rip hypothesis, where the universe expands and expands and expands, and it becomes just so far apart that gravity and all the other forces can't hold it together, and then eventually even the atoms are pulled apart from each other. It's the big rip. Everything is just kind of disintegrated, scattered, and it just ends. There's the big freeze, where the universe expands, and as it expands, it just keeps cooling and cooling, and cooling, and eventually everything in the universe is so far apart and so cold that everything reaches absolute zero, all molecular motion ceases, and that would be the heat death of the universe. Pretty not very. It's not interesting. It's very sad. There's the big crunch where gravity eventually takes over, collapses the universe back into a singularity. And my favorite one, although there's really no evidence for any of these, it all kind of depends on how much mass there actually is in the universe. And we're only really starting to figure out what dark matter is, or if it even really exists, if it's just some error in our calculations. We don't really know. So speculating on these is it's fun. Let's leave it at that. The one that I like best, that doesn't mean it's true. Nature has no obligation to work the way that we want it to. But the one that I like best is the big bounce, where gravity collapses everything back down into a singularity. And then there's another big bang and we start over. Maybe exactly the same path over again. It'd be nice to be able to do things a little bit differently. But anyway, that's the one that I favor. And that's the end of the universe. And at that point, we have to stop because that's the end. So thank you, everybody, for all of your efforts, all of the things that you put into this semester. I know things were difficult, and I appreciate you for sticking with it. I had a lot of fun teaching the class. I hope that you enjoyed it as well. And really just remember that oceanography is this interdisciplinary science. It's where all of these different aspects meet. We talked about geology, we talked about biology, we talked about physics, we talked about astronomy a little bit. All of these things are oceanography, this interdisciplinary science. And again, just thank you. That's all I've got for the lecture, and that's all I've got for the course. Good luck on the final, make sure you're there, and I will have a good life. Live long and prosper.